Well, in our last talk of the session, let's switch gear to look at the internet. Our presenter, Petros Gigis, is a final year PhD student from Computer Science Department of University College London. He's working with Professor Stefano Visiciu and Professor Mark Hanley. His research interests include computer networks, routing, and internet measurements, and he's on the job market. Please go ahead.
Thank you for the introduction. As you may wonder about the title, I will start with providing some context why we picked that title. So let's see a topology consisting of three ASs. And let's take the perspective of AS1. AS1 expects traffic from AS2 to traverse the direct link as this generates profit. However, traffic from AS2 may reach AS1 through AS3, and this can be either a misconfiguration or maybe AS1 failed to advertise the route to AS2. In that case, the operator in AS1 can use packet counters and find that the traffic is coming through an ingress point that looks unexpected. What in reality can happen is that we may see traffic with source IPs of AS2 coming through AS3, and this traffic can be spoofed. In that case, the network operator, if he only relies on packet counters, he will start troubleshooting a network issue that doesn't exist. So the question is, how can we distinguish if it's a routing issue or it's just spoof traffic? And unfortunately, control plane techniques cannot solve this problem. And the only solution is to look on the data plane. And in this work, we look for legitimate traffic. And by the term legitimate traffic, we refer to traffic that originates where it claims to be from. So the idea is that if we are able to detect legitimate traffic, we can use it as a routing signal, and we can build a monitoring tool on top of this that alerts us only when legitimate traffic is ingressing at unexpected locations. So the question that naturally arises, how we can distinguish legitimate traffic from spoof traffic? And is it easy? The short answer is not easy at all, as the traffic that we see can be affected by multiple factors. These factors include external network conditions, for example, packet loss, the implementation of transport protocols, but also cases where malicious users send different traffic patterns. However, there is a fundamental difference between legitimate traffic and spoof traffic. And this lies in the fact that legitimate traffic usually consists of some closed-loop flows. And by the term closed-loop flow, we refer to a flow that the sender sends some data to the receiver to elicit a response in order to send more data. So the big idea in this work is that if we are able to find closed-loop flows, we can use them as a proxy to detect legitimate traffic. So again, the question is, how can we detect closed-loop flows? And the short answer is that we can tweak traffic and try to get some feedback from the traffic. So in order to do that, we first need a module. We will call it checker. And in this example, the checker is in the path between the sender and the receiver. We know that the paths on internet are highly asymmetric, so we expect checker to see only one direction of a flow. So the idea is that if a checker tweaks the traffic through the path sender to the receiver, the traffic will reach the receiver, and then the tweak action will propagate back to the sender, and finally, it will come back to the checker. And by definition, a closed-loop flow protocol is TCP. So we consider that TCP is the best candidate protocol to do that. And the question that comes up is, what is the simplest action that we can do in TCP in order to trigger a well-defined action? And that is, we can just drop a data packet, as we expect TCP to retransmit the data as by definition, it ensures the reliable retransmission of the data. So is it that simple? So we just drop a packet, and if we observe a retransmission, we consider that the flow is closed loop. If we don't, we consider that the flow is not closed loop. Unfortunately, not, as there are many things that may go wrong. First, the retransmission packet may follow a different path than the one that we monitor. In that case, if we only rely on a single packet drop, we will consider that the flow is not closed loop. On the other hand, maybe a malicious source sends duplicate packets in order to mimic legitimate retransmissions. And again, in this case, if we just solely rely on a single packet drop, we are going to consider that the flow is closed loop. So it becomes obvious that the signal from a single packet drop is weak and noisy. And the question is, how can we improve this? And we can improve this by dropping a few packets until we get enough confidence on the nature of the traffic. And here comes our system Penny. Penny is a traffic checker with a statistical model as its core, consisting of two competing hypotheses. The first hypothesis is that the flow is closed loop, and the second hypothesis is that the flow is not closed loop. Penny randomly drops packets with an equal probability, and based on the outcome of its packet drop, it gains confidence in one of the two hypotheses. Once one of the two hypotheses dominates the other, Penny reaches a conclusion. And our models consist of counters, parameters, probabilities, and we take into account cases that the packet may miss our monitor, or maybe a malicious source sends duplicates. And in order to give you an intuition how the maths work, here is how the two hypotheses evolve as the packet number increases. We can see in figure A where we have not closed loop flow, but as the number of packets increases, the hypothesis 1 tends to 0. And on the contrary, when it's closed loop, the hypothesis H2 tends to 0. So this sounds pretty straightforward, and we have made the assumption so far that we can perform enough packet drops in order to gain confidence in one of the two hypotheses. But this assumption lies that we always have enough packets to drop. And normally on internet, we have a lot of short flows. And in this case, in order to apply Penny to short flows, we can use the same statistical properties and apply the packet drops across multiple flows. The model maintains the same properties, and also the impact of the packet drops is minimal, as we drop at one packet at max per flow. And in order to bring Penny from theory to practice, we found that although it's an easy idea, there are a lot of complications. First of all, there are complications regarding the TCP protocol as itself. For example, if we drop a packet, for how long we should wait for a transmission? And do we expect the transmission packet to be exactly the same with the packet that we drop, or it may contain fresh data? And another complication is that what if we drop a packet and we observe a reset packet? Then we have the network conditions. And what if we have packet loss and we have retransmissions that are not triggered by Penny? And what if while we run Penny on the flow, suddenly the routing changes and we stop seeing new packets coming? And finally, we assume that an attacker may know exactly how our model works and eventually try to mimic retransmission in order to bypass it. In order to handle all these complications, we came up with a lot of mechanisms. And for this mechanism, the fine details matters. So in the next slides, I will explain some of these mechanisms. The first mechanism has to do with the retransmission. So we drop a packet, and the moment that we drop the packet, we store the current measurements. Then we apply a conservative expiration threshold of 3 seconds. And during this expiration threshold, we can either observe a transmission, or if a timer hits, we didn't see a retransmission. And after that, we can evaluate our hypothesis based on the current measurements. But what if we drop a packet, and while we wait for a transmission, we observe a thin packet? In this case, we consider that any packet that precedes thin should be retransmitted. So this is a valid packet drop, and if we don't observe a retransmission, probably it's either not closed loop, or we may miss it. And in this case, again, we evaluate the hypothesis using the new counter values. And on the contrary, we may drop a packet, and while we wait for a transmission, we observe a reset packet. In this case, we cannot be sure if a TCP stack retransmitted the packet or not. So the only solution that we have is we should discard any measurements that we have so far and roll back to the previous packet drop. And another complication has to do with duplicates. Let's assume that a source sends a packet, and immediately after the packet, it sends a duplicate one. So if we drop the first packet, we will think that the second packet is a retransmission. But this can be true. This can not be true, because the source sent it like twice the same packet in a row. Should we just discard any retransmission packet that we observe? The question is that we cannot do that, because we expect to see duplicates, as duplicates may be the outcome of downstream losses of our monitor. So we introduce a threshold on the maximum number of duplicates. We expect TCP to be able to cope with a certain amount of loss, and after a point, the TCP cannot make any progress. So we pick a threshold of maximum duplicates packets of 15%. And given this threshold, if an attacker knows exactly how Penny works, he cannot duplicate more than 15% of the packets. So it's still very hard to guess which packet we dropped in order to send the retransmission packets. So the question that comes is, does Penny work? And in order to test this, we evaluated using the NS3 simulator. We tested multiple TCP variants, diverse network conditions, including upstream, downstream losses, mixed case scenarios. We also tested different input of traffics, like only closed loop, only spoofed, mixed scenarios. And we also evaluated different parameters of Penny. And I will start with the results. Here is the case that we have only closed loop flow. In this diagram, the x-axis shows the number of packets that we have seen, and the y-axis indicates the number of packets that we drop. Each orange dot represents the outcome of our statistical model, And as we can see, in every case, Penny reports that the flow is closed loop. Next, we try to understand how Penny works when the traffic is only spoofed. And we consider that the worst case scenario is someone to know exactly how Penny works and sends duplicate packets just below our threshold. So we consider that we have a spoofed traffic, and this spoofed traffic contains 14.9% duplicate packets. As we can see in this figure, we have gray and blue dots. Blue dots indicates that Penny reported a spoofed flow outcome, and gray that the duplicate exceeded. As we can see, with low number of drops, we may misclassify the spoofed traffic as closed loop. And this lies on the fact that as we rely on stats, with low number of drops, we may get it wrong. So in order to deal with this, we consider a very conservative threshold of 12 packet drops. So Penny, before reaching an outcome, drops exactly 12 packets. And as we can see, using this threshold, the outcome of Penny is always correct. And finally, we tested cases where we have mixed traffic, like we have closed loop flows plus spoof traffic. And we can see that we get either spoofed outcome or closed loop. And getting the closed loop outcome is fine, as it aligns with our goal of detecting legitimate traffic. But in the case of spoofed outcome, we can just switch to track individual flows. And then we are looking for at least one closed loop flow on the aggregate. We also evaluated what is the performance of our packet drops. And we saw that if we carefully pick the packets that we drop, the impact is minimal, especially in the cases where we drop over an aggregate of flows. And finally, we also tested the feasibility of our system, and we found that as we mostly update counters, Penny has low processing requirements and memory. To summarize, I presented Penny, a robust, reliable, and practical traffic checker that interacts with transiting packets to access if they are part of legitimate and hence no spoofed TCP flows. We have seen that by dropping a few TCP packets, we can get a very strong signal. And if we carefully pick the packets that we drop, the impact of them performance can be negligible. So we hope that network operators will find Penny as a useful tool to improve their visibility in traffic ingressing into their network. Thank you, and I'm happy to take questions.
Okay, thank you. Yeah, please go ahead.
Thank you for your interesting talk. This is Chang Liu from Tsinghua University. Do you think your method will cause a performance degradation on legitimate TCP flows because it causes packet drops, which will cause illusion of congestion to especially congestion algorithms that are loss-based? They will shrink congestion windows.
Yeah, so we drop at max 12 packets. And in the case of Penny, we consider that these drops are across multiple flows. So imagine that we have an aggregate of 100 flows, and we pick 12 flows to drop a packet. And we saw that the impact on the individual flow is similar to the 1% loss. And in the case of aggregates, we saw that there is no distinction. So we just drop one packet from the flow. And if you apply the packet drop after the slow start, the impact is even less.
Okay, thank you.
Thank you so much for your talk. I'm Cheyenne, first year PhD from UNSW. So probably I'm missing something very trivial, but what about UDP?
That's a very good question. And we consider that on the internet, there should be always some TCP traffic. And another question is, what about QUIC? And for QUIC, we consider that we can modify the current approach. And as QUIC encrypts the direct packet load, we cannot distinguish retransmissions from original packets. And the only solution is that we can drop the handshake packet, or we can play with a spin bit.
Right. Yeah, maybe we can talk more later. Thank you.
Thank you.
Okay, let's take one more question.
Darryl Veach, University of Technology, Sydney. You described how to get around the problem of flows that are too short to be able to drop many, that you drop across many flows, also less aggressive. But what about if the spoof traffic is only in a small proportion of flows, so that your overall signal will be low and you won't, isn't that a major problem? You're really assuming that a fairly high proportion of flows are being spoofed. How do you control for that?
So, can you repeat the first part of the question?
Because you're splitting your drops across many flows, you won't get a spoof detection unless, in the case where only a small proportion of flows are being spoofed.
Yes, but we are interested in detecting legitimate flows, closed-loop flows. So, in order to, we care only to find a closed-loop flow outcome. So, if we end up on a non-closed-loop outcome, we then switch to individual flows.
Yes, but
Maybe we can take this offline?
no, hang on, I'll just finish because this is the point, right? But you won't know to switch to individual flows until you already have some confidence that they are spoofed.
Yes, we will have the outcome that it's spoofed, and then we switch to the individual flow testing.
Okay, maybe offline.
Yeah. Okay. So with this, well, let's thanks Petros again.